This is chapter 1 of the Belk text entitled The Process of Science. This is going to be a brief overview of chapter 1, The Process of Science. You will be responsible for the chapter in its entirety, but herein you will find highlighted a few key concepts. This chapter covers the process of science, which is really a very methodical method by which scientists make discoveries, analyze data, and draw conclusions. This will then lead us to what exactly is hypothesis-driven science. The third section in your text highlights the basics behind analyzing results obtained from experiments. And the fourth section is evaluating scientific information. We'll not be discussing that in this video as it is adequately covered in your text. In answering the question, what is science, it's important to highlight that science is both a body of knowledge as well as an agreed upon systematic method of inquiry. Science can further be defined as the observation, identification, experimental investigation, and theoretical explanation of natural phenomenon. This process of inquiry is largely driven by curiosity as well as interest. It is that natural ability to make observations and ask why that's highlighted in your assignment that accompanies this chapter entitled The Art of Observation. In this chapter, we are highlighting hypothesis-driven science as opposed to discovery-based science. In discovery-based science, we are answering the question of what, such as what new medicines can be found in the rainforest, or what types of bacteria inhabit contaminated groundwater. Hypothesis-driven science, on the other hand, answers how or why. Hypothesis-driven science is also known as the hypothetico-deductive method or the scientific method. With hypothesis-driven science, we make observations and measurements, and then we set up experiments where we systematically manipulate the subject to answer a specific question. Ultimately, answering the question of how or why is the basis of hypothesis-driven science. Hypothesis-driven science, also known as the scientific method, includes 5 key steps. The first step of which is observation, also sometimes coming from discovery science or experimental results. The second step is the hypothesis step, in which you make an educated guess or an explanation for your observation. The third step is experimentation and prediction. This is when you test your hypothesis by predicting the outcome of an experiment. Fourth, it's data collection, in which you collect and analyze data. Sometimes things go as planned, sometimes they do not, at which point you then can draw your conclusions. And your conclusions either support or refute your hypothesis. We do not say that they prove or disprove, but we rather use the term support or refute. Let's work our way through the scientific method together. As stated in the previous slide, science often starts off with an interesting observation. These could be simple things such as, if every fall I notice that the maple tree in my backyard loses their leaves. How about in your own life? Can you think of 1 or 2 observations as it relates to diet? Are there certain foods that you feel more energetic or less energetic after consuming? Are there certain foods that make you feel a certain way? Pause the video here for a second and try to write down 2 or 3 observations in your own life as it specifically relates to diet. For myself, I know that I sleep very poorly at night when I drink coffee after 4 p.m. It's just a basic observation. After having made your interesting observation, science will then proceed by making a hypothesis to explain the observation you previously made. So for example, we observed that maple trees lose their leaves in the fall. We need to come up with a hypothesis that might be able to explain that process that we observed. My observation was as it related to diet. I know that I sleep poorly at night when I drink coffee after 4:00 p.m. I should be able to come up with 1 or 2 hypotheses that might explain that tendency. Again, what I'd like for you to do is pause the video and come up with 1 or 2 methods by which you might be able to explain your observation that you made as it relates to your own diet. Please write out 1 or 2 hypotheses at this time. So what might a hypothesis look like for the observations that we've made? So, for example, the fact that leaves fall off in the fall, our hypothesis might be that cool nights cause leaves to fall off of trees. As it relates to the observation I made about my diet, my hypothesis might be that caffeine causes me to stay awake at night. What about you? What about the observations you made about your diet? Take a moment to solidify the hypotheses that you made. When writing a hypothesis, you need to keep several key things in mind. First of all, hypotheses are strong statements. They must be clear and they must be precise. Secondly, hypotheses must be testable. They have to be material in nature. They cannot test the supernatural. Things such as colds are generated by an accumulation of negative karma. Those cannot be tested. You must be able to evaluate your hypothesis through observations and experimentation. So hypotheses must be strong statements. They must be testable. Lastly, hypotheses must be falsifiable. There has to be a way to prove whether or not it is. So once you've made your observations and written out a thoughtful hypothesis, this then leads you to the next step of the scientific process, which is experimental design. So let's do that. Let's design an experiment to test our hypothesis that cool nights cause leaves to fall off. When we're designing an experiment, you need to include several key variables, the first of which are controlled variables. These are the conditions that theoretically could vary, but you are purposely going to keep them constant to the extent possible so that they do not affect the outcome. Secondly, the variable that we do want to manipulate is the independent variable. This is the variable that you are going to be changing in the experiment. We also always need a dependent variable. This is what you're actually measuring in the experiment. This is something that's likely to change based on the presence or the absence of your independent variable. When you're doing experimental design, you should also keep in mind a few other key concepts. One is it should be a controlled experiment, such that you are testing the effects of only a single variable. You also, if possible, should include controls. This might be a subject who is not exposed to the experimental treatment but has all the other variables the same. If you're doing an experiment involving lots of people, it'll be very important to include random assignment as well. This is an effective way of assigning individuals to groups for testing in an unbiased way. So let's get back to our experiment and observation, in which we made the hypothesis that it's the change in temperature to colder nights that causes leaves to fall off in the autumn. So our hypothesis will lead us to designing a particular experiment, which we should also then be able to predict possible outcomes. So what is an example of a prediction that the cool nights hypothesis, where leaves fall off of trees, makes? So one possibility is that we could conclude if we are able to somehow keep temperatures constant, that would result in the leaves not falling off of the trees. So again, a useful hypothesis is able to lead you to make predictions about your experimental outcomes. So again, our hypothesis that the change in temperature to colder nights causes leaves to fall off of trees in the autumn leads us to a prediction that we can then put as an if and then statement. If cool nights cause leaves to fall off of trees, and if two groups of trees are kept in similar environments, but one group is kept at constant temperature, while the other is brought to a lower fall-like temperature, then the leaves will only fall off the second group of trees. As you can see, our hypothesis has allowed us to make a prediction about our experimental outcome. Predictions allow us to make these accurate conclusions based upon our experimental results. Tests, if they are to be useful, they have the potential to show whether your hypothesis is false. Because of a good prediction, we can know what to expect if the hypothesis is supported, what to expect if the hypothesis is rejected, and if there are any flaws in our experimental design. So let's go back to our hypothesis. Our initial observation was that leaves on maple trees fall in autumn when the days get colder and shorter. Our hypothesis was that colder temperatures of autumn cause the leaves to fall off of trees. So what is our experiment as shown here in number 3? Small maple trees are grown in 2 greenhouses where the only variable is temperature. We are going to keep the soil the same, the food the same, the amount of light the same. The only thing we are varying in this experiment is temperature. So our control group is going to be kept in warm, summer-like conditions, and our experimental group is going to be allowed to have temperatures in which it's going to be able to fall down to somewhere between 30 and 40 degrees Fahrenheit, which is what one would see in the fall. So now looking at step 4 here, what if these were our potential results? So our control group and our experimental group look identical. What would this then cause you to conclude? That our hypothesis must be rejected. Clearly, it's not a change in temperature that causes leaves to fall off of trees, because as demonstrated in the data analysis, the amount of leaves dropping off the trees is the same for these 2 groups. So we can then look at our hypothesis and say we must reject our hypothesis. It's not just the colder temperatures of autumn that causes the leaves to fall off of trees. So what are some alternative hypotheses and test them? What could be a different hypothesis to the fact that leaves on maple trees fall in autumn when the days get colder and shorter? Maybe it's not due to temperature, but rather it's due to the amount of sunlight. Perhaps it's the shorter amount of daylight causes the leaves to fall off of trees. So this time what we can vary rather than temperature is let's vary the length of light that the trees are exposed to. So again, we have identical conditions in the 2 greenhouses for these trees. The only variable here is the amount of light that these 2 greenhouses are exposed to. So now let's say we get the following data. What you see is that the control group, in which the amount of daylight is remaining the same for 200 days, has very few leaves dropping off of the trees. But our experimental group, in which the amount of daylight gets progressively shorter for 200 days, you see that the number of leaves falling off the trees dramatically goes up. In conclusion, what we can say is we can accept our hypothesis. Our hypothesis was supported by our... Here we should briefly highlight the difference between a hypothesis versus a theory. In the scientific world, a hypothesis is really a proposed explanation for a natural phenomenon, as we've stated. These explanations are based on either previous observations or experimental data. It requires some testing, and then you can make some testable predictions. This is in contrast to a theory. So in the scientific world, a theory is really a broad explanation of some aspect of the natural world. This explanation is substantiated by a large body of evidence. It incorporates observations, hypothesis testing, and laws of science and nature. It's considered an established set of ideas that explains a vast amount of data and offers valid predictions that can be and have been tested over time. So once we've designed experiments and obtained vast amounts of data, we then need to analyze the data to determine whether or not our observations, hypotheses, experimental design, and our conclusions are truly significant or not. So the way that we determine their significance is based upon statistics. So statistics in science, they are used to evaluate and compare data. We can extend the results from small samples to an entire population using various statistical tests. Whether or not something's considered statistically significant is based on results of differences between groups, and it's due to random chance and not merely an error in experiment. So some key ideas when we're looking at statistics is this idea of the mean, which is merely the average of the replicates within a group. Another key idea is your sample size, the number of replicates, so often referred to as your N. We also need to understand the idea of variance, which is the degree of scatter of your replicate data, as well as standard deviation, which is just a common measure of the variance in a particular data set. So for instance, if we wanted to look at the mean and standard deviation for two data sets, what I want you to do is look at data set 1 versus data set 2 and pause the video and figure out what's the mean or the average for data set 1 as it compares to data set 2. Now that you've determined the average is the same for these two groups, you should have gotten an average of 10 for both groups. My next question to you is, which data set do you expect to have the greatest standard deviation? Data set 1 or data set 2? So pause the video for a second and think about that. So now that you've looked at your two data sets that have the same average, which is 10, you should be able to look at data set 1 and realize that the numbers as it relates to the average, which is 10, are much closer to that average. The numbers in the data set 2 vary much more greatly around the mean. Variation about the mean is a key concept in understanding statistics. So as you can see here, these three data sets shown in the red, the purple, and the blue all have the same mean, which here is demonstrated as 10. The data for the red group is much closer to the mean, so we say that the variance is much smaller. The variance around the mean for the blue group is much greater as it compares to the red group. So when determining statistical significance, it's much more likely that the red group is going to have a higher level of statistical significance than the blue group. Here we have some data taken from your book for two different experimental groups. We have a control group and an experimental group, and this experiment was run twice, as shown as experimental 1 results and experimental 2 results. What you can see is that if you're looking just at the light blue group, which is our control group, the average for this group is actually identical. If you look at the experimental groups, again, the averages are identical. However, the confidence interval, which you can think of as your variance around the mean, are very different. In experiment 1, the variance around the mean is very small. So what this is showing you is that the results, which for control group, the average is shown as about 8.2 or 8.3, that actually maybe goes as high as 9 and as low as 7.5, but the variance is quite small. However, if you look at the control group in experiment 2, you can see that the variance around that mean is huge. So you might have seen numbers as low as 5.5 and as high as 11.5. So even though the averages were the same, the variance around the mean is vastly different. So if we were going to argue at face value which data set is more statistically significant, you could argue that the first experimental group is more likely to be statistically significant. So lastly, in understanding statistics, you should always keep in mind what is your sample size, You want to have a large sample size. Bigger is always better, and you're more likely to detect statistically significant results in your two population groups if your sample size is large. Thank you so much.